Hi all, welcome. My name is Arnab Biswas. I'm a data scientist at the eco-energy business of Carrier Global Corporation. Today I'm going to talk about automated feature engineering for large-scale time series data using two Python libraries, tsfresh and Dask. Let's start with the definition. In time series, we capture the value of a variable repeatedly over time, resulting in a series of data points indexed in time order. The most important characteristics of time series is the value of a variable at any particular instance of time is dependent on the values from the previous instances. That is, there is a natural temporal ordering in the data. Now, the most important characteristics of time series brings the biggest challenge, the temporal ordering. Traditional machine learning algorithms are not designed keeping time series data in mind. So if I feed a series of numbers representing a time series to a machine learning algorithm, probabilities are very high that the algorithm will not be able to decode the information hidden inside that temporal ordering. Then there are other challenges. For example, the nature or the pattern of the time series changes over time, making it non-stationary. Time series data may go noisy. Generally, in an industrial environment, we use sensors to capture time series data. If a sensor goes faulty, it starts picking up a lot of noise, reducing the signal to noise ratio. Often, what happens for any time series task, like a forecasting or classification, we have not one time series, but multiple time series. And these time series, they may have different sampling frequency or different length. Finally, time series comes from different domains. The nature or pattern of the data changes from one domain to another domain, from one use case to another use case. To address these challenges, we use something called feature engineering. In feature engineering, we try to capture the most important characteristics of a time series into few metrics. For example, here I have a long time series with 60,001 observation. I can start representing this time series in terms of few metrics like mean, median, maximum, minimum, etc. That way, I compress a raw time series into a shorter representation. And this is necessary. This is necessary for the machine learning algorithms, which may not be able to decode these numbers, but the machine learning algorithm may be able to understand the information extracted in the form of these features. Next, the question is, what are the features do I need? Generally, we start with the standard generic features, which helps us to summarize the data, and then we move into the domain specific features. Again, within the same domain, the features which are relevant for one use case may be completely different from the features relevant for another use case. So as a data scientist, it's our duty is to generate as many features as possible, and then using cross-validation mechanism, select the most relevant features. This is where a library like tsfresh comes into picture. tsfresh is an open source Python library. Using tsfresh, we can automatically generate 750 plus features from one single time series. And the nature of the features vary widely. There are features which are related to descriptive statistics. There may be features which are related to the scientific background, like digital signal processing. And of course, there are features which captures the historical nature of the time series data. Out of the box, tsfresh provides feature selection mechanism as well. However, we are not going to talk about feature selection mechanism today. We are going to focus on the feature generation process. Next, let's extract few features using tsfresh. For this, I have picked up some data from a Kaggle competition called INGV Volcanic Eruption Prediction. The data consists of a large number of CSV files. Each CSV file contains 10 minutes of logs from 10 different sensors placed around a volcano. We call each CSV file as one segment. This is how the content of one segment file looks like. There are 10 time series. Each time series is associated with one sensor. Next, I pick up a bunch of time series and append them. Sorry, I pick up a bunch of CSV files and append them in a pandas data frame. For the sake of simplicity, I pick up just two time series related to sensor 1 and sensor 4. This is how the aggregated data or appended time series looks like. It has data from various segments, and within one segment, the observations are sorted based on the column called time. Next, I pass these pandas data frame into the extract feature function of tsfresh, and tsfresh generates a bunch of features. What tsfresh has actually done, it has taken all the time series which are there for a particular segment and then generated all the relevant features and placed them in one row. As a result, my extracted feature data frame has one row per segment ID. For two time series, tsfresh has generated 1558 features. That means for one time series, it has generated 779 features, which is huge. Let's take a look at a few of the features which tsfresh has generated. Here are the features related to sensor 1. There are basic features like maximum and minimum, and then there are features, more complicated features like C3. To be very honest, I don't understand all these features, and probably that's the point. There may be features which are relevant for my task, but which I am not aware of, or which I have not been able to identify during my research works. But those feature works, and that's where tsfresh adds the value. We should note that tsfresh also generates features based on rolling data. Now, if the size of the time series increases, we start hitting two types of problems. One, large execution time, which is a compute bound problem, and we start feeling the need of large memory, which is a memory bound problem. To address the compute bound problem, we should utilize multiple cores or processors which are available in a CPU inside a single machine. If the resource available in a single machine is not sufficient, we should use distributed computing. To handle larger than RAM data, we should opt for one of the following options. First, we should try to slim and trim the data so that it fits into the memory. If that doesn't work out, we should upgrade our RAM to a larger size. If that's not an option, we should use something called out-of-core computing. Out-of-core computing is a concept used by Dask, so let's try to understand it. In out-of-core computing, the data rests in the hard disk. At any point of time, we pick up one small portion of the data or few partitions of the data, load it into the main memory and do the computation. Next, we come back and pick up few other partitions from the hard disk, load it into the main memory and do the computation. And the process goes on. At any instance of time, we are not loading all the data from the hard disk into the main memory. That's how out-of-core computing handles larger than RAM data. If none of these options are working out, then we should use distributed computing. What are the challenges which we face while doing data science with large data? Popular libraries like NumPy and Pandas, they are not designed to scale beyond a single core or processor. They are not designed even to scale beyond a single machine. If I have a data which is larger than RAM data, then these libraries cannot be used. These libraries expect the data to be loaded into the RAM for computation. This is where Dask comes into picture. Dask is an open source Python framework which parallelizes the Python ecosystem. Using Dask, we can utilize multiple cores, which can be in one machine or which can be distributed across multiple computers. Dask handles large data using out-of-core computing. Dask works well in multi-node cluster or 100-node cluster. At the same time, Dask works in a single instance VM or on a laptop. The good news is, out of the box, tsfresh addresses the compute bound problem or the memory bound problem. If the data fits into the main memory, that means if we can load the data into a pandas data frame in a single machine, tsfresh utilizes multiple cores available in that machine. tsfresh can distribute the feature extraction process to a clustered environment. tsfresh handles larger than memory data utilizing Dask and PySpark. However, I'm not going to talk about all these today. Rather, I'm going to talk how I utilize best of both the worlds. I use tsfresh to extract the features from time series data, and I use Dask to parallelize the feature extraction process as well as to handle larger than memory data. Let's start with the basics. This is the Dask architecture. The client is an interface using which user can interact with a Dask cluster. The Dask cluster consists of a scheduler and multiple workers. The scheduler actually doesn't do any computation. It distributes the tasks to the workers, which does the computation, comes up with the final result, sends back the results to the scheduler, and the scheduler in turn sends back the result to the client. The scheduler and worker, they may be located in one machine or they may be located in multiple machines. If the client, the scheduler, and the workers are located in one machine, we'll call that as a local cluster. Here, I have created a local cluster in this VM with 8 workers. Next, I have created a Dask client and connected that client to the cluster. Now onwards, any computation related to Dask happens in this cluster by these multiple workers. Next, I have asked Dask to read few CSV files which matches with this particular regular expression. Looks like there are 4 such CSV files, and Dask reads these files very quickly within 119 milliseconds and returns us back a Dask data frame. But in reality, Dask has not actually read any CSV file yet. It has created a plan which we call as task graph to read the CSV files. The Dask data frame looks similar to a pandas data frame. However, it has 2 additional things. One is called partition. It has 4 partitions and it has 4 tasks. To understand what is a partition, we have to understand how a Dask data frame is constructed. A Dask data frame, represented by the gray color, is nothing but a wrapper on multiple pandas data frame. The pandas data frames are represented by black. Each pandas data frame, in our case, is associated with one segment or one CSV file. Since we have 4 CSV files, we have 4 partitions. Next, if we invoke the method called visualize on this Dask data frame, we can see the task graph. This is the plan which Dask have to read all the CSV files. One of the worker will pick up one CSV file, load the data into a pandas data frame. Now this happens for all the 4 CSV files by multiple workers in parallel. Next, we'll see how we can parallelize a custom Python function using Dask. This is a custom Python function, and I invoke this custom Python function on this Dask data frame consisting of multiple partitions and parallelize the process using map partitions API. This is the corresponding task graph. So one of the worker will pick up one of the CSV file, load the data into the main memory in the form of a pandas data frame, and then invoke this particular method or function on that pandas data frame. And here at the end of the process, we'll have the result available. Now this happens again for all the 4 CSV files by multiple workers in parallel. We call this methodology as embarrassingly parallel. I'm going to use this methodology to parallelize tsfresh's extract feature function. Finally, when I invoke the method or function called compute, then Dask actually executes the task graph, computes the result, loads it into a non-Dask data structure like pandas or NumPy, gives us back the result to the client. Next, let's try to parallelize tsfresh's extract feature function using Dask. Here, I'm asking Dask to read all the CSV files which are there inside the train directory. There are 44331 such files, hence the Dask data frame has 4431 partitions. This is the custom Python function. This custom Python function is nothing but a wrapper on tsfresh's extract feature function. By setting n_jobs to 0, I have shut down tsfresh's internal parallelization mechanism and I have allowed Dask to take over. Finally, here I am invoking the custom Python function on this Dask data frame and parallelizing the entire process using map partitions API. At the end, I invoke a method called toParkway. The moment I invoke this method, Dask starts executing the task graph. Dask for each segment file, Dask loads them into the main memory in the form of a pandas data frame, extract the features, and then writes the extracted features back to the hard disk. Next, let's take a look of the Dask dashboard. Generally, it takes some time for the workers to pick up the tasks and starts executing it. Let's wait for the workers to start working. Here, each horizontal line represents one worker. There are 8 workers and hence 8 horizontal lines. It shows each horizontal line shows the tasks which each worker is executing. Different tasks has different colors and the name of the tasks are shown here. Next, we move to the workers tab. It shows that there are 8 workers. The CPU usage of the workers are pretty high, above 90%, but the memory usage is considerably low. This is because of the fact that Dask is doing out of core computing. So one of the worker at any instance of time is picking up one of the segment files, loading it into the main memory in the form of a pandas data frame, then using tsfresh's extract feature function, extracting the features, and finally writing those features back to the hard disk. Then the worker goes back and picks up the next segment file and it continues the process. That is how Dask is parallelizing the entire process by using multiple workers, and at the same time using out of core computing, Dask is handling larger than memory data. With this, we come to the end of this session. Here are few references which I have used, and this is the place where I have saved the slide as well as the code. Hope you have enjoyed the session. Thank you.